Welcome back to Machine Translation. Today we're going to look at current challenges. So it's basically open problems for neural machine translation. Let me preface this with a comparison of neural machine translation and statistical machine translation. This is results from the news translation share task at the WMT 2016 conference. This is actually the only year I can show a slide like this because that was the only competition where both statistical and neural machine translation in significant numbers participated. In this competition, different groups could build systems and then translated a previously unseen test set of about 3,000 sentences of news content across various languages. We're showing here, I think, German-English translation. The machine translation systems are then evaluated in terms of the blue score on this axis here. But since these are very, very different systems of different type, it was also always interesting to also do a human evaluation to kind of ground also the validity of blue scores to compare machine translation and also be a bit more fair toward systems that may be disadvantaged by the blue score. So here's one example actually for that. So this system receives a relatively low blue score, one of the lowest blue scores, although it's kind of middle of the pack otherwise. And then that's because it's a rule-based system. They're typically fairly accurate, but not very good at producing language just as fluent as neural machine translation systems, and they get often punished by that in terms of blue, although humans don't really can tell the difference. So the difference in terms of blue scores in neural machine translation does not really show up here. So you can pretty much see a straight line here for most of the systems. Most of the systems kind of fall into this. And you see in the red here, the neural machine translation systems that outperformed the previously best statistical machine translation system. As I mentioned in the previous lecture, actually syntax-based machine translation systems were at the forefront back then. So a year later, pretty much every large provider of machine translation switched to neural machine translation. That's also why I can only show it for 2016, because 2017, hardly anybody still bothered to build statistical machine translation systems. Here is a similar claim from Google about the benefits of neural machine translation, and they already have this rather scary comparison against human translation, where for French English, it is almost reaching human quality. That might be a somewhat questionable claim, but there's definitely a clear difference between what they deem the quality of neural machine translation systems versus phrase-based machine translation system. In 2018, there's even more hype. So this is the year where Microsoft Research famously claimed human parity and then qualified what human parity is quite a lot. There's another provider that claims cracking Russian to English neural machine translation, and so on. So 90% of the system's output labeled as perfect by professional Russian English translators is one of the claims in that story. So one concern is, and this is an actually interesting finding from 2017, where they compared a more fine-grained human evaluation. One is adequacy, do actually get the words translated correctly, and the other one is fluency. And we see a big gain for neural machine translation systems for fluency, but not necessarily gains for adequacy. So they gain in some of the language pairs, but not in all of them. And that's clearly something that is well understood that neural machine translation is much better at. It is actually able to produce grammatically correct, fluent output sentences, while previous phrase-based models that relied on a statistical n-gram language model were often good at producing output that was fluent locally, but maybe overall in the sentence structure was rather incoherent. Okay, so it's not always good, and that's what today's lecture is about. So we look at various challenges for neural machine translation. Obviously, there is many, many more I could list here. These challenges are mostly picked because, in contrast to statistical machine translation, where maybe neural machine translation systems still struggle compared to statistical machine translation systems, and that also pinpoints to areas where neural machine translation theoretically could improve because prior uh, modeling techniques were able to get better results. As I said, there's various other things I can mention. I'm gonna go through all these. I just want to point out I'm not gonna talk about interpretability today because I will cover this in next lectures completely. Uh, it's going to be completely committed to interpretability and interpreting the working of neural machine translation systems. So one grand challenge we really have with neural machine translation is that it is accurate often, but sometimes it makes mistakes. But whenever it makes mistakes, we really have absolutely no way of knowing why it makes these mistakes and what did go wrong, and we can't really fix it very well. More on that, as I said, in the next lecture. Let's start with the first of these topics, lack of training data. Here's a chart that actually got quite famous about that compared phrase-based neural machine translation performance and neural machine translation performance on an English-Spanish data set, pretty much the same that was used for the WMT news task translation competition, but it varied the amount of training data from about 400,000 sentences to almost 400 million, words, 400,000 words to almost 400 million words. And this is a striking observation. So this is a phrase-based statistical machine translation system that was just trained on the parallel data with no additional monolingual data. What is typically done, of course, in phrase-based MT is that we build a big language model, and if you add a big language model, you also see clear improvements. So that's a relatively flat curve when contrasted to the curve for neural machine translation. So that starts in really horrible territory. But then here in the order of around maybe 10 million, maybe 100 million words, starts to outperform statistical machine translation and finally surpasses it. So that also means that more data helps. So being able to train neural machine translation models on more and more data is generally seen as there's still, it hasn't plateaued yet. There's still gains to be had. So if we double the amount of data, we could end up maybe somewhere around here. I don't know where that is. Maybe that's 32. Okay, so that is a pretty striking result. There's definitely a lot of interest nowadays in this part of the curve and the low resource machine translation because partly for a lot of applications, machine translation is good enough. In terms of web page translation, if you just want to know what's going on, what's happening in the story, what's happening on this web page, um, the machine translation quality is good enough. It doesn't have to be perfect for that. It's good enough. But it's not good enough for many language pairs where we don't have much data. So maybe the top 50, top 100, maybe somewhere in that, we have enough languages, we have enough data, but for the thousands of other languages that are spoken around the world, we don't have enough data. Here are some examples of machine translation output of this English to Spanish system at different amounts of training data. So these are basically corresponding to the systems in the previous slide. So this is the lowest resource system where 1,000 of the training data is being used, while this is for the output of a machine translation system where all the training data is used or just a 30th of machine translation is being used. The translation is actually the same going forward. So here's the sentence: a Republican strategy to counter the re-election of Obama. And at the bottom you see a perfectly fine translation. I don't speak Spanish, but Spanish is similar enough to English that we can pretty much say, okay, it talks about Obama, it talks about the re-election, there's some kind of contra-action or something, and there's a strategy and a Republican strategy, and these look like the right function words more or less there too. So this is a perfectly fine translation. And once you go towards lower resource, you see how things fall apart. So here, or you see words like Ohio instead of Obama. The first sentence also doesn't have Obama. Obama it really just shows up here. Here you talk words about explosion. Here is an I can only guess an organ of coordination for the announcement of free determination. I'm just guessing here, but this has very little to do with the input. So this is typical output of a machine translation system that is not trained on enough data. It produces probably relatively fluent output, but it has absolutely no relation to the input at all. So all it managed to learn at this point is the kind of language model decoder aspect of a machine translation system where it is producing fluent output. The next topic where neural machine translation systems is shown to be inferior to previous statistical machine translation system is domain mismatch. So here's just a result chart to explain you what's going on here. So we trained machine translation systems on different corpora. Here, corpora of law text. Here's a corpus of medical text. Here's a corpus of IT. Here's the Quran, so religious text, and then a subtitle corpus. And then we have test sets, and in this chart, in this box here, we have a system trained on law and tested on law. We then have blue scores in green again for the neural machine translation system, and in blue for the statistical machine translation systems. And they perform somewhat similarly. The neural system, the statistical system is slightly better, but if you look at other corpora, for instance, the Quran, no, actually they are also, but in no IT, here you see that the neural system actually outperforms the statistical system. So that's a bit of a mixed bag. It's also better here. But if you look at all the other cells in this table, so this is where we take a system trained on the law corpus and then evaluate it on medical. You see drastically inferior translation quality, so 12 against 18. Some other cells that are kind of worth pointing out is like things completely fall apart for a neural system. While okay, the translation quality for the statistical system is not great either, but is dramatically better. So neural machine translation system seems to get out of whack when you shift towards a new domain and it's confronted with input that it hasn't seen before. Here are again some examples. So this is a sentence from a subtitle corpus. So the source sentence is schau dich herum, which means look around you. And here are the various outputs. So if you train on all the data, it does the right thing. Actually, if you train on the subtitle corpus, it also does the right thing. But for everything else, you kind of see also how neural machine translation and statistical machine translation kind of breaks apart. So look at the system trained on the Quran, and you see, well, C is in there, or look is in there, U is in there, but it just kind of models it together, while NeuroMT comes up with the output, take heed of your own souls, which is very much in the spirit of the Quran. But it's a bit hard to tell that that has anything to do with the input. Here are some other examples. IT, so shower, it doesn't even have in the data, so it just copies it, and then by itself, it just kind of puts some rubbish there. NeuroMT produces switches to pause. I think the more drastic one is the medical, where it just comes up with this kind of title of a medical corpus document. Has absolutely no relation with the input, while the statistical system, yeah, there are two words that are not translated, but then the other words are actually fine. And overall, if you would actually, if they would have been translated correctly, uh, this would have been fine. The words are, although not translated, they are in the right spots. I can't even fathom what this means. Okay, next topic look at is rare words. So more frequent a word is in training data, the more likely we're going to get it right. At test time, that is not surprising. The more training data you have, the better you do. We already kind of alluded to that. The question now is with the words that are only occur like 1 or 2 or 3 or 4 times. Let's actually look at that. So um, we have to check this correctly. There are two things we have to do. We have to look at the frequency of input words in a test set. So you can basically have to check for all the input words, how frequent they are in the training data. And then we have to figure out, are they correctly translated? This does require some word alignment. So it's not super easy to do, but if you just run word alignment on the source of the test set and the machine translation output, you can do accurately enough. So here's some of the gory details. So we actually have to generate word alignments between input and output words and hope they're correct, that we produce correct output word alignments. Then we look up the count of the word in the input. Then we have to figure out what it was translated to by the machine translation system. And then we also have to check, is that the correct translation, the reference translation. Here we just check if that word is in the reference translation at all. So there's a lot of tedious special cases we have to deal with, like what do you do with one-to-many alignment, and so on and so on. So what if only some of the output words are on the reference, and so on. Anyway, leave that aside. These are things to deal with. So if you want to do the study correctly, um, you have to address all these cases. Details for that are in the book. Here is the result of this. So again, green is neural machine translation and blue is statistical machine translation. And then both mixed together are this kind of cyan type of color. Here are the very frequent words. So this is where more of the translations are correct in the neural output. And here are the words where the cases where the statistical system has a higher accuracy. What can also happen is that a word gets dropped and we just see throughout that more words are dropped by the neural machine translation system. Okay, so what do we observe? We do observe actually, these are words that never occur in the corpus and we still get them 50% right. How is that possible? Well, a lot of these are names and numbers, so they're not that hard to get right. And then these are rather rare words, and actually for lower frequency words, neural machine translation is holding up pretty well. So this doesn't really give much evidence to the concern that neural machine translation is bad at low frequency words. Let's move to another problem, which is word alignment. So we already looked at this in the previous lecture, and we're actually going to look at it again in the next lecture. This is the attention mechanism, and it compares here in blue. The blue boxes are alignments produced with IBM-style word alignment, and the green are the relative probabilities computed by the attention mechanism. And in this example here, it does generally do the right thing, and therefore we can actually take the attention mechanism and use it as kind of to report word alignment. Sometimes you want to report word alignment. There are several use cases where having the word alignment is a useful additional output of a machine translation system. Just to give you two examples, one is obviously for debugging, what happened or how did it came up with this translation. Another example is what if there would be a bold tag around Obama and Netanyahu, and I want to reinsert the bold tag around that. So I need to figure out that just because there was a bold tag around here, I basically have then go through the word alignment and say, yes, I have to put a bold tag around that. Those kind of things. Okay, so this looks all pretty good. Here's another example. So this is a different training run. We're now translating from German to English, and the word alignments are all whacked off by one. Why did that happen? I don't really have a good answer to that. It's a bit of a mystery. It's a artifact maybe of the LSTM recurrent neural network that is being used there, that certain information might be stored in memory states versus the output state, and who knows. But it does happen and it's quite frequent. So these are all completely wrong word alignments. In the meantime, since we moved to transformer models, I should say that especially since we have multiple layers of transformers and multiple layers of attention, word alignment has become much, much less accurate and useful. Uh, so the attention mechanism is really not revealing the information that we need for word alignment. So this has become now a completely open problem, how to actually get proper word alignment out of a neural machine translation systems. So here's an example where a recurrent neural network model is just giving you completely wrong word alignment, and in transformer models, uh, the the attention mechanism is much more blurred all over the place. Also, if you have multiple attention heads, they might do all kinds of weird different things, and it's much less reliable. Let's move to the next topic, which is beam search. So one thing we can do in beam search is change the size of the beam. And in statistical machine translation, this is a sure thing to do. At some point, however, the trade-off between decoding time and quality is really not worth it anymore and things plateau. However, with neural machine translation, we observe if you increase the beam size, translation quality actually gets worse. There are two different uh, 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 things plotted here. One is using unnormalized scores. So this looks at the different translations that are being produced, and what's reported as the best translation is the one that has the highest score, or if you frame it in terms of probability, it has the highest probability. However, this measure prefers sentences that are short simply because fewer numbers are multiplied to each other. And this is especially bad if you open a wide beam, then more and more shorter sentences are being produced and they get preferred, and that gives you worse translation performance. So what's typically done is that we normalize the score by the length of the sentence. So we take the score and then divide it by the number of words. That gives you a flatter curve, but still it dips off. So beam search seems to be doing a decent job, at least for this particular system, on this particular test set, up to about a beam size of 100, but it's not really doing better than with a beam size of 12. Um, that's the same blue score. But once you have a higher beam size, it also deteriorates. So this is a bit of a puzzle. Why does beam search fall apart? So one reason is shorter sentences, but that's not necessarily then the case for this example. Um, Maybe one suspicion that I can throw out here that applies to everything we talked about so far is neural machine translation generally seems to be less comfortable when it's confronted with unusual situations. So obviously, if it's low resource, then any new input sentence is rather different from the training data, or often very different from the training data, and it just doesn't know what to do with it. If you give it an out-of-domain sentence, that's also different from anything it's seen in training, and it doesn't know what to do with it. In beam search, when we widen the beam, we feed in as a prefix not quite the words that the model would have preferred, so it also gets into a somewhat unusual state. So what seems to be the case that neural machine translation is just not as robust as statistical MT. Let's look at another topic. This is a bit of a longer topic where we look at noisy data, especially noisy training data. So here is a finding from the old paradigm of statistical MT. We have data, like here is a fairly large corpus from, again, this WMT news translation competition. German English, so 90 million words. It's pretty high quality data, lots of it Europol, but also news, commentary, stories, and so on and so on. And then we threw in web crawl data, and of course, things improve. However, if you do the same thing for neural machine translation, the score plummets. And here's a breakdown. What happens if you just add 5% more data of noisy quality? So this is now measured 5% of the original data. So you have 90 million words originally as clean data. And now you add 5%, so 5% of 9, so 4.5 million words. Noisy data, slight gains, 10% of noisy data. Neural NT already falls down. 20% of noisy data, additional data. So the clean data stays the same all the time. You're just adding noisy data. Things collapse. And then if you put in as much noisy data as the clean data, so you double the data size, we see this collapse in quality. So that triggered a lot of interest in corpus cleaning methods. I'm citing here one paper that is one of the early papers that was motivated by this research. But we'll come back to this in a future lecture on crawling the web for data where corpus cleaning has become one of the key contributions to make this successful. So here we are more interested in why is this happening? What kind of noise is harmful for neural machine translation training? And here are some suspicions. What if the noisy data has a lot of misaligned sentences where the source and the target are both pretty decent sentences by themselves, but they're just not translations of each other? Maybe you try to align documents that are actually not translations of each other, or when you align the sentences in the documents, some mismatch occurred and you're mismatching the documents. Another one is disfluent language. What if there's just bad language in there? Maybe a bad translation, maybe it's some ancient machine translation system that's being used. Who knows? Wrong language data, maybe the corpus also contains French text, either as source or target, in a corpus that purports to be German English. Maybe they're untranslated sentences where some of the material is the same in source and target. That happens very often on web pages where only part of the web pages are translated and the rest kept the same. Maybe the navigational elements are all the same, or maybe only the navigational elements are translated. Then there's also a lot of discussion on short segments. If you have a lot of short segments, maybe that hurts training. And then a mismatched domain, which we already discussed. So we basically tested these different kinds of noises and see how much they actually hurt performance. So we're gonna do the same thing here again. We keep the clean data as we have it, and we add additional noisy data, and we're just gonna add different kinds of noise. So we add 5%, 10%, and 20% of sentences where the source and the target is shuffled, and then see the impact on translation quality. So here, when we add 50% of sentence pairs where source and target is shuffled, it really still has absolutely no impact on the statistical machine translation system, but the neural machine translation system gets significantly harmed. If we add as much misaligned sentences as there are clean sentences, yeah, it starts to hurt the statistical system a little bit, but not nearly as much as it hurt the neural machine translation system. So having misaligned sentences in your parallel corpus is definitely harmful for neural machine translation model training. At this step, maybe throw the comment that it is one of the hopes of machine learning that it is robust to noise, that when it sees a lot of noisy training examples, that can generalize enough to then ignore the noise, but this is clearly not the case here. Here is another example of misordered words. So here we just basically add sentence pairs that are perfectly fine sentence pairs, but we shuffle words in the sentence rather randomly. And we can do this on the source sentence, we can do this in the target sentence. So if you do this in the target sentence, it kind of equally hurts statistical and neural machine translation. However, if we do it in the source, at least at the 100% level, it hurts neural machine translation more. Here is now the real killer. What if you put in untranslated sentences? So there are two types. We have here, as I said, a German-English corpus. So the source sentence is German and the target sentence should be English. But what if the target sentence is just a copy of the source sentence? That really leads to detrimental performance of the neural machine translation system. It hurts when you do it at the 100% level. It hurts statistical MT too, but for anything lower, it has hardly any impact. If you do it on the target side, so if you take target side text and copy it into the source, it generally doesn't hurt either statistical or neural machine translation. So why is this happening? So others observed this as well. So this is referred to sometimes as copy noise. What if you have copy noise where source sentences are just copied into the target? And one finding is actually that this has actually also a strange interaction with beam search. Okay, let me explain this. So when you do beam search, the model explores different translation options. And it might actually prefer a perfectly fine translation at the beginning, but then as a second choice, it also just might do the copy. If you would just do greedy search, it probably would prefer doing perfectly fine translations all the way to the end. Each of the time, though, it has always choices to make, and maybe it is here. In this case, it's 80% certain, and here it's 70% certain. So it kind of will follow through the path, and you multiply all these numbers, which is how you score the different paths. You get then at the end a fairly low number because there are many, many possible translations that are all acceptable. So, however, if you copy, maybe it doesn't like to copy. It's very unlikely to copy, gives it low probability, but then if it kind of keeps copying, if it just is in the mode of copying, it can be very sure about how to continue. If its goal is to only copy from things from here on, it's just always sure. So at the end, you end up here with 10% probability. So people have worked on that and also came up with some remedies how to fix this in decoding. Here is another example where we just put in French as part of the parallel corpus. So the top example here is, so it's a German-English corpus, except that we also add some French-English sentences. That has hardly any impacts at all. But then we put it to the target, and yes, there it does hurt. Performance, again, it hurts. Neural machine translation slightly more than it hurts statistical machine translation. Maybe you're surprised here when you have 100% wrong language corpus. So here you have as much French English as German English. Well, of course, if you put in a German sentence, it's probably still going to recognize the German sentence translated correctly. But what's happening here? So here you have as much German English as German French. Why would it be so inclined to still produce German English? And that is maybe due to domain mismatch or something we never really tracked down properly. Okay, here's short sentences. This is just basically good news, no harm done. If you just put in really, really short fragments, so if you just dump in dictionaries. So if you just put in really short stuff, yeah, we can see some degradation, but generally it doesn't hurt things too much. Okay, the last point I want to raise is control over output. So sometimes in a neural machine translation system, you want to give the model the opportunity to follow certain guidelines that we impose on the translations. We already discussed this at some point. So sometimes we want to override the decisions of the decoder. We brought this up in the context of decoding for neural models. So why do we want to do this? I think the most common one is terminology. People have terminology lists. Often translators work with terminology lists that says in our corpus we use this word, and that's the word you're gonna go use. Um, and just to give you one example, maybe you have equal probability to produce output like liberty and freedom, and they both really mean the same thing, but maybe one client says, no, no, we have to talk about freedom. That's the word we want to use. So whenever you have a German word like Freiheit, which might translate to either of these, don't let the neural machine translation system make its decision. Always go with freedom. So you want to override the neural machine translations decisions, how to translate words. What we might also have is a rule-based component that deals with numbers and quantities that, for instance, translates 2.5 centimeter into 1 inch as part of the translation process. And we just have that's very easy to do with a rule-based component. And then we just have to make sure that the neural machine translation system follows that. So we wanted to use that as well. So we already talked about this, as I said, in the decoding session. So one method that was developed for statistical machine translation was this markup scheme, which says, can you translate this word here, router, as also router in German, instead of so that the technical meaning of a computer router versus maybe other more general meanings of the word router, where you actually might have a German word for it. Or here you have also other things where you say this here is a brand name which has to be translated in one piece. That's what meant by this zone here. They can't move around. They have to stick together. You can't just produce a translation where psi goes to the beginning of a sentence and this goes to the end of the sentence, and other words are in the middle. So this is a markup scheme that is really easy to integrate in decoding for statistical machine translation. Here you just, for pre-specified translations, you just override the phrase translation table and saying the only phrase translation you can use here is the one that is specified, and we eliminate everything else. And these zones and walls actually also just means this has to be translated before we're translating the rest of the sentence. These are also relatively simple constraints to be followed by just really limiting limiting reordering in the model, in the decoding process. There might also be other constraints that we might have. So here's just a few examples where just by the translation task and the applications, we might have additional, more formal constraints. So there's not vocabulary choices, but other properties of the translation. So let's think about subtitles. So if you have movie subtitles, we already have the movie subtitles. We now have the subtitles in one language. You need to put the subtitles into the other language. So there we have the problem that the translation has to fit into the space of the screen. So if the screen has particular real estate for the subtitle and it has a sentence in there, then the translation we put in there can't become longer than that. Otherwise, it's not going to fit in there. So we might limit the length of the translation. That's something that actually our machine translation system should then do already out of the box. Another thing is that if you actually have text and it's broken up into lines, so if you have a longer sentence, it might be broken up into multiple things, maybe even multiple frames where it occurs. Then we have to merge it before translating, and then we kind of have to figure out how to break that up again into meaningful lines that somewhat correspond to the content of what is shown on the screen at any given point in time and in the translation. And that's a tricky problem as well. Here's another area where we might have constraints. Speech translation. Well, we first have to deal with the problem that the input is often not well formed. It's just some rambling, free-formed speech, which is often not very grammatical. Another challenge is if you actually want to do real-time translation. So while I'm talking here, if I would be talking live and you would listen to this live, then maybe the translation should also already start at the beginning of a sentence before I actually finish the sentence. So that's an interesting challenge as well. If you translate it and then display it as subtitles, you have to be careful that you don't produce too many and too long subtitles that can't be read. So we don't just flash subtitle at people to cover all the material. Very often subtitles are shortened, so they actually don't have the entire content of what's being said, but kind of reduced to the essential content. That's something you have to do then in the translation as well. An interesting challenge is also dubbing. So if you actually would now do the whole end-to-end speech recognition, translation, and speech synthesis, where you actually produce audio at the end, you also want to match the audio to the mouth movement. So if the speaker kind of opens the mouth and at that particular time some audio plays of the translation, then the translation can't have something like a p or a m where the mouth is closed. So this is something that skilled dubbers do really well, and you really immediately notice it in dubbed video where this is done badly, because it seems like often the audio is still playing while the person on the screen already closed the mouth and is done talking, and that's something really obnoxious. Okay, here are some other examples. Poetry. So maybe you have to follow a certain meter. So you only have 10 syllables and the stress is on the third and the fifth syllable, things like that. And rhyme. So if you translate something that was rhyming to begin with in the source language, you have to produce output that is also rhyming. And how do you do that? So there's all these constraints you might want to impose. And it's not at all clear how to impose any of these constraints on neural machine translation models.